So today we're going to talk about what are called phase changes. And so to do that, we first have to learn about what the phases are. So there are several states of matter and three very common phases that we find on Earth: solids, liquids, and gases. And you're probably familiar with those. And then there's two more that are a little more uncommon. We don't find them on Earth too much, but they're kind of cool. But for our purposes, we're going to focus on the solid, liquid, and gas phase, which is what we commonly encounter here on Earth. So in order to understand phases, we have to understand what is called the kinetic molecular theory of matter. So the kinetic molecular theory of matter is the theory that explains the behavior of matter, and particularly its states, solids, liquids, and gases, in terms of the kinetic or movement of molecules. So kinetic molecular is the movement of molecules. So let's take a quick look at what's going on with solids, liquids, and gases. So here's a simulation which shows a gas. So in the gas, the particles are all free to move in any direction. When they bounce off of each other, they collide elastically without losing energy. They take up all the space that's available to them, and they're in motion. And they don't really stick to their neighbors. There might be forces between these guys, but they're not big enough to make a difference. Okay? So that is what we consider a gas. Now, if we take energy away, this gas, the molecules will start to slow down. And as they slow down, they turn into a liquid. Okay? And the reason they turn into a liquid is because there are small attractions between the molecules. And when they're not moving fast enough, those attractions become important, and they can kind of hold the molecules to each other. So here's kind of a simulation of a liquid. They're free to move around, but for the most part, they're all huddled together at the bottom of the container. And once in a while, you see an extra fast moving one flying off, but it's a liquid. They're still free to move, but if you cool them down even more, then they turn into a solid. And when you get a solid, then they're still moving because they're not absolutely at absolute zero, but they're only wiggling in place. So you can see here that these guys are still in motion, but the motion is not enough to overcome the bonds that are holding them together locked in place. So this is what we call the kinetic molecular theory of matter. And if you take a solid, for example, and you start adding energy, the molecules move faster and faster and faster. And when they move faster and faster, they eventually can break the bonds that hold them together, and they can turn into a liquid. And if you add enough heat, the bonds that hold them together even a little bit in a liquid become unimportant because they're moving so fast, and they turn into a gas. Okay, so that's what we call the kinetic molecular theory of matter. All right, so solids are generally characterized by a couple things. First of all, they have a fixed volume and a fixed shape. The molecules are connected together with their neighbors in rigid bonds. So if this molecule here is next to that one, it'll stay next to it. And there's many different kinds of bonds that hold these together, and you spend a lot of time in chemistry learning about those kinds. There are molecular bonds, covalent bonds, which are the van der Waals force. There are ionic bonds, there's metallic bonds, there's amorphous solids. And we're not going to really worry about all those. All we're going to do is realize that when a material is a solid, it means that the bonds are strong enough to keep them in place even though they're still trying to move and wiggle and jiggle. Liquids, on the other hand, don't have a fixed shape. They'll take the shape of their container, but they do have a fixed volume. The molecules are attracted to each other weakly, but their attraction is not strong enough to lock them into place given their motion. So when you make something warmer, it starts to move faster and faster. And in a liquid, they're moving fast enough they can't get locked in place, but they still kind of hover around each other. Okay? A fun fact here is that sometimes corn and sand are solids, but in large quantities they can approximate liquids. So be careful. One of the common ways to die on a farm in the Midwest is to fall into a grain bin. So corn or soybeans look like a solid, and each individual particle is a solid. But the solids are not locked in place relative to each other. They're free to move. And if you were to jump into a big bin of corn, you would actually sink just like you would sink in a fluid, and you'd become entrapped and actually suffocate. So a common way that people die is they jump into corn to do something or think they're being funny or goofing off, and they can actually sink. So that's called grain entrapment. All right, lastly we have gases, and gases don't have any fixed volume or fixed shape. The molecules are moving very fast, so they don't really attract or stick to their neighbors. If they do happen to bounce into their neighbor, they're moving so fast they rebound elastically. And whether something's a solid, liquid, or gas at a given temperature all depends on how strong the bonds are. If the bonds are really strong, you've got to heat it to a much higher temperature to make the molecules move fast enough to break those bonds. So this is what we call the phase change chart. This basically is a schematic showing the transitions from different phases. And you probably know these, and you're welcome to pause the video and make a copy of this in your toolbox, which might be a good idea. But when we transition from a solid to a liquid, we call that process melting. When we transfer from a liquid to a gas, we call that process boiling, or more commonly, vaporization. So vaporization is converting or transforming from a liquid to a gas. And if we go the opposite direction, if we go from a gas to a liquid, so you have some condensation when you go from a gas to a liquid. And if you go from a liquid to a solid, we call that freezing in the case of water, but in general, we call that fusion, okay? So fusion, freezing, same thing. There's a couple other special ones I don't have on here. You can go directly from a solid to a gas, and that's what happens with dry ice, for example, and that's called sublimation. And you can go directly from a gas all the way back to a solid also, and that's called deposition. But again, those are more uncommon, and we're not going to worry about them right now. So understanding the names of these transitions is important. So take a minute to jot that down if you need to, so you have that chart in your toolbox. All right, so the question is, what happens to water when we boil it? So you can try this at home. All you need is a meat thermometer and a pot of water on the stove. You can, I've got a video here that takes a while to play that I'm not going to play right now. But the idea is, when you turn the burner on, the water starts getting warmer and warmer, and the temperature goes all the way up to 100 degrees Celsius. But when it gets to 100 degrees Celsius, it won't change anymore. And you should try this. Stick a thermometer in a pot of boiling water and watch it for a while. I mean like a meat thermometer, not your COVID thermometer. When the water starts to boil, the temperature reaches 100 degrees and it stays there the whole time. And as it continues to boil and you continue to add heat, the temperature does not go up anymore. It's stuck at 100 degrees. But what's happening is water is boiling away. The level of the water will keep decreasing. So you can try that on your own. But that's an example of a phase change. And what happens when substances are changing phase is that we are adding energy, but the temperature does not change. Something else is going on. Okay? So here's a visualization to kind of see what's going on. What I've got to do, I got here a cup of ice, and it's on a stove, and we're starting off at a solid. So the temperature is negative 50 degrees Celsius, which is way below the temperature at which ice melts. Ice will melt when this gets to 0. And so we're going to look at this chart right here, and you might need to run this a couple of times to see it. But when we start off heating this, the temperature starts at negative 50, and you can see the temperature is rising. We're up to negative 6 now. We're going from negative 50 on this chart up to, we're at negative 6 right now. And if I keep adding energy, you can see as I'm adding energy, the temperature is not changing. I'm adding energy, but what the energy is doing is it's turning the solid ice into liquid water. So it's undergoing a phase change. So while we are changing phases, we are adding energy. So Q, right here, see this is a Q versus T graph. Q is increasing. We are adding energy, but the temperature is stuck on 0. What's happening is the ice is melting. So there it goes. It melts, melts some more, melts some more, melts some more. And now you can see, I'll pause it again. The temperature is still 0 degrees. So we've added a whole lot of heat, and that heat, that energy, has turned ice into water, but the temperature hasn't changed. The temperature will not change until all the ice is melted. Once all the ice is melted, now you'll see as we add heat, the temperature is going to start going up. Okay? And so we continue to add heat, the temperature goes up. We are now on this part right here, which is what we're used to. Q equals mc delta T. The change in temperature is equal to m times c, the heat we add is mc delta T. And the temperature keeps going up, and we call this a liquid. And the temperature will keep going up until we get to 100 degrees. So this chart's a little small here, but right when we get to 100 degrees, the temperature will stop going up. Okay, so you can see now we're at 100 degrees and the temperature is not changing at all. And we keep boiling this, we keep adding energy. This is still moving to the right, but the temperature is not changing. What's happening is energy is being added, and these particles are breaking free of the water, and they're leaving. They're turning into a gas, okay? And so that's what we mean when we say the temperature does not change during a phase transition. We're adding energy, but the energy is going into changing the phase, to breaking the bonds, not making them warmer, okay? So that's the idea. So this is the chart we're going to use, and we're going to actually sketch some of these in our book. So this is kind of the basic chart that becomes important. When we have a solid, a liquid, and a gas, the heat versus temperature graph. So on this axis here, we have the temperature, and on this axis here, we have the energy we've added. And so if we start with a solid that is really cold, like minus 50 degrees for ice, and we add energy, it'll get warmer. It'll get to minus 40, minus 30, minus 20, minus 10, until it gets to 0. And this special temperature, marked by this bottom blue line, that is the melting temperature of the substance. So for water, that's 0 degrees Celsius. When the temperature reaches 0 degrees Celsius, right here, we have ice at 0 degrees Celsius. If we then start to add more heat, the temperature does not go up. The temperature stays the same, but we are melting the ice. So over here, the temperature is still 0 degrees, but now it's all water. So what did we get for all the energy we added? We didn't get any extra temperature. We got the melting of the ice and turning it into water. Now, once it's all melted and we just have water, if we continue to add energy, now the temperature of the water will increase. It'll go to 30 degrees, 60 degrees. Eventually, the temperature of the water will get to be 100 degrees, and then something else happens. As we add energy, again, the temperature doesn't change. See, this is flat. This is the temperature axis here, and we're staying the same temperature, 100 degrees. But as we add energy now, our water is turning from a liquid into a gas. And once it gets over here, it is all of a gas. And we can then heat it up forever until it becomes a plasma, which we're not going to worry about. Okay? So the idea is when you are on one of these slant sections where the temperature is changing, then the amount of heat is equal to MC delta T. But when you are on one of these flat sections, when the temperature is not changing, the amount of heat you have to add is equal to M times L, where M is the mass, and L is a constant, which tells you how much energy it takes to break the bonds. Okay? So when the phase is changing, when we are on a horizontal plateau, we are changing phase. And the energy it takes to change the phase is given by M times L, where L we're going to look up in a table. Okay? So this section right here is all water at 0 degrees, but it's in different phases. At this end here, it is solid at 0 degrees. And when we get over to here, it is now liquid, still at 0 degrees, okay? And to get from here to here, we got to take M times L. Likewise, on this section of the curve right here, at this point right here, the water is liquid at 100 degrees. Right here in the middle, it's half liquid, half gas. And all the way over here, it is all turned into a gas. So it is still 100 degrees, but it's a gas. And then from that point on, if we continue to add energy, the temperature will rise again. So this is the equation, which is in your toolbox, and you can check and make sure it's there. When we are changing phase, so not when we're warming it up, but when we're changing from one form to another, from ice to water, from liquid to gas, the amount of energy it takes is given by M times L. And L is just going to be a constant we look up in a table. Now, you're going to have to figure out which constant to use, though. If you are melting it, that's called the latent heat of fusion. So fusion is melting or freezing, and that's when you transition between a solid and a liquid. If you're transitioning between a liquid and a gas, we call that vaporization, and you will use LV. So the table I'm going to show you in a minute has both LF and LV in it. You've got to know which one to use. So if you're melting water, you're going to use LF. If you are boiling water, that's changing it from a liquid to a gas, you're going to use LV. Okay? So here's the table. This is the third of the 3 tables you've seen linked in your homework. And it's the one that tells us a couple of important things for a bunch of different substances. So let's just take water because we're familiar with water. So right here for water, the first thing it tells us is the temperature at which it melts. That's 0 degrees. Then it tells us how much energy it takes to melt it. So this 3.3 times 10 to the 5th, that's how many joules it takes to melt a kilogram of water. Okay, so that's what we call the latent heat of fusion, L sub F. Over here it tells us the boiling point, the temperature at which it changes from a liquid to a gas. And then the last column tells us the latent heat of vaporization. This is how much energy it takes to turn the liquid into a gas. Each kilogram takes 2.26 times 10 to the 6 joules of energy. Okay? So a sign convention, if we're going from a solid to a liquid, we have to add energy, and so L sub F is positive. If you're going to go from a liquid to a solid, you have to remove energy, and so we make L sub F negative. So you just got to remember to get your signs right. If you're going to the right on our diagram, you're adding energy. If you're going to the left, you're removing energy, and you just got to remember that make L positive or negative. Okay, so let's do an example problem or two. I've got 0.25 kilograms of ice, and it's at 0 degrees. And I want to know how much heat it requires to melt it. So I'm going to turn it from a solid into a liquid. So the first thing we got to do is we got to find water, because that's what we're dealing with. Right here's water. It melts at 0 degrees, so we are already at 0 degrees, but it's ice. And we have to turn it into a liquid. And so this is the L we're going to use right here, because we're going from a solid to a liquid. And so you can write, if you want, heat fusion is solid to liquid, vaporization is liquid to gas, but this is the number we're going to use right here for L. So there's our line we're interested in, since our substance is H2O. Here's our generic diagram, and so we need to sketch on here where the transition just happened. So when we have ice at 0 degrees, we are right here. That is ice at 0 degrees. Okay? It's a solid, so the left-hand side is solid. Over here is ice, but it's been melted. It's still at 0 degrees, so really it's water at 0 degrees. And so for this problem here, we are going from here to here on our little diagram of Q versus T. Okay, so that's the section we're interested in right there. And in order to find out how much heat it takes to move horizontally on this graph, we need L, the latent heat of fusion, which we got from our table, and we need the mass, which is 0.25 kilograms. And then to calculate how much heat we need, we just take M times L. Okay, so in this case, you take the mass, 0.25 kilograms, times 333,000 joules per kilogram, and that gives us 83,000 joules. So it takes 83,000 joules of energy to take 0.25 kilograms of ice, which is already at 0 degrees, and melt it so that it turns into 0.25 kilograms of water. Okay? Now, we have not changed the temperature. We simply melted it. In the next problem, it's slightly different. What if we have an ice cube at 0 degrees, and I want to melt it and then warm it up to 22 degrees. So remember, if I have ice at 0 degrees, I'm starting right here. Going from here to here will melt the ice, but then I need to go up to 22 degrees. So it's going to look something like that, and then like that. That's the two steps we're going to do. We get to figure out how much energy it takes to do this, and how much energy it takes to do that. Okay? Since we're dealing with ice, we can look up the latent heat of fusion for water. We already know that. It was in the previous problem. Once we get the ice turned into water, we're going to warm up the water. So the water is going to go from 0 degrees to 22 degrees right here. And so we need the heat capacity of water. And then to figure out how much energy it takes to do this, that's M times L. And to figure out how much energy it takes to do this, that's MC delta T. So that's what we've already been working with, MC delta T. So the total energy is going to be ML plus MC delta T. So you can plug in all those numbers. Here's M times L, and then here's MC and delta T. It went from 0 to 22. And you can plug all that in, and you can figure out it takes 10,600 joules to convert the ice cube from ice into melted water at room temperature. Okay, so that took two steps. We had to melt the ice, and then we had to warm it up. So you're going to solve a bunch of problems in your homework today. We're going to calculate how much energy it takes to change the phase of a substance. And what I really want you to focus on is making good diagrams like this. Okay, so sketch your diagram. Use the table to figure out what the melting and the boiling temperature is, and sketch that on your diagram. And then sketch which part of the diagram we are traversing as we solve this problem. Okay. So just think about those, and then you're going to solve some problems and give you some practice with this. All right? Okay. Good luck.